that you have a wrong number of dimensions. That's it.
And if the number of dimensions of space is just wrong, I can't take it seriously.
That's it. I mean, he
But see,
literally
this
said
to
that in
me
a
is so
conference.
crazy. It's so
Yeah.
insane. But when you tell me that there are other popular books discussing the cosmological constant problem, sorry, I haven't seen a single one that does a job at actually trying to explain it. That's something that every string theorist actually agrees on, and this is why it annoys me.
Welcome to Phymaths podcast. Today, our guest is Thomas van Riet. By the way, I don't know how to pronounce Riet or Riet.
Riet, actually.
Riet. Okay, Riet.
Yeah, it's
Thomas
a
van
long
Riet.
E, Riet. Yeah.
Riet. Okay, thank you. So our guest is Thomas van Riet. He's a theoretical physicist at KU Leuven, Belgium. And today we will talk about different topics regarding string theory and string compactifications and some other topics regarding that. So I want to start from one of your positions where you say that not being if string theory is not able to get deSitter, it's not a bad thing after all, which is actually something that a lot of people don't agree with. So the thing is that suppose that if it happens that string theory is not able to get deSitter at all, so should we assume that string theory is wrong, or should we assume that our universe is not deSitter or something like that?
Okay. So let me start by answering by first saying what the word means. String theory is wrong. So string theory is not cannot be wrong. It's a theory. I think by wrong you might mean is our own universe a solution to string theory? I guess that is what you mean, right?
That's what I mean. Yes.
Yeah, I think that's an important thing to add. This nuance is actually absolutely crucial. So okay, to answer your question, say we have a proof that there are no deSitter solutions in string theory. Okay, there are two options in that case. So one option is that indeed string theory cannot describe our universe as we see it today, or we don't fully understand our universe. I think both options are equally valid at this point. There seems to be overwhelming evidence for some kind of acceleration, cosmic acceleration going on in the universe right now. But then again, if you look at the discussions in observational cosmology, it's also fair to say that this field is full of confusion, right? The Hubble tension is one good example of this. Also, when we say string theory doesn't have deSitter, when we say the word deSitter, what we really mean is a space for which there's at least a finite volume of spacetime. In that space should have exact deSitter isometries, right? So the expectation of cosmologists is that dark energy will remain constant in energy density, because that's the definition essentially, and all of the rest in the universe will dilute, so that we will reach deSitter. Now there's no deSitter. Let me be clear on this. There's a lot of matter still in the universe, so that this isometries are clearly not deSitter-like, but it seems like they will become more and more deSitter-like. Now the question is, no deSitter in string theory, does that rule out? And you assume deSitter the universe will be deSitter soon. Would that rule out string theory? I'm not sure, because maybe string theory forbids the exact deSitter isometries, but not almost deSitter isometries. So in more technical terms, the discussion I think should be about what is the equation of state parameter of dark energy, right? So when we say imagine one day we have a proof there's no deSitter in string theory, it rules out omega. So let me call, or let me say W. W is the usual symbol for it. It would rule out W equal -1. But if you speak to observational cosmologists, they will give you a window for W, right? And it's only -1 that has these special mathematical isometries. Okay, so I think it could very well be that that's forbidden deeply in string theory or any theory of quantum gravity. But whether string cosmologists will, whether observational cosmologists should really narrow it down to exactly -1, I would find that really strange, to be honest. Yeah.
Right. Okay, so one thing that some people say that, and probably I think I also read that in one of your papers, that what we observe is probably not long-term acceleration, but some effect of inhomogeneities in space. So that's also something that's possible,
Well,
right?
I haven't studied this, so I'm only referring to papers that have claimed this. So, indeed, I think it's crucial to be open-minded to the question of dark energy, and this is a highly complicated question of data analysis, which is for sure not my expertise. So again, I want to emphasize that there's a big majority of observationalists that say, we see a clear, almost exponential expansion of the universe. But you should also be aware that there are people who are doubting this, right? And you mentioned one of the options, that is indeed that we feed this, the observationalists feed in as an assumption that the universe is homogeneous and isotropic. And then you make the conclusions you make. But imagine that we're living in a special place in the universe. Indeed, it could be that there's what we see some kind of an effect of inhomogeneities. I would say there's a lot of people that should be mentioned here, and I'm not the expert, probably I shouldn't, but a person that has been always pushing our community to be more open-minded is Sarkar, who just retired from Oxford University. And he's been one of the people pushing, he's actually making a claim that there's no dark energy at all. Yeah. But again, I think it's important in science that one, of course, has to look at what the majority says, and that matters probably more. But we should also keep an open mind that there are serious people out there who are willing to even question dark energy, by itself, that it even exists, let alone whether the equation of state parameter of dark energy is close to -1. Right.
Right. Okay. So the thing is that we know that there might be some dark energy. I mean, for more than 20 years now. So do you think that and string theorists have tried to work a lot on getting deSitter out of string theory. But do you think that string theorists have lived up to the problem of dark energy or no?
That's a difficult question. I think I can make your question. Let me apply it more general. Did string theorists live up to string phenomenology as a whole, to phenomenology as a whole? And phenomenology for me comprises cosmology and particle physics. Well, I would say we should be more patient. Right? Obviously, so the real issue, as you know very well, is that string theory is very hard to calculate with. And it's important to realize that this is not a problem of the theory, but this is how it is presented, but that's obvious bullshit. Okay?
Yeah.
What is obvious that if you have a theory which is a very simple equation, okay, yet super hard to calculate with, it's our problem, not the theory's problem. Okay, we just are not good enough in mathematics. In this, maybe in 100 years from now, we're much better in mathematics and we can do it. And so the moment you ask about specifically cosmology, time dependence, that's when we break, for sure, supersymmetry, which is a symmetry part of superstring theory. And that's when we become bad at mathematics. Okay, so humanity became great at the mathematics of string theory on the condition we do not break supersymmetry within string theory. So it's a symmetry of the theory, but of course, solutions of a theory do not need to obey the symmetry of the theory. That's obvious, right? I mean, the symmetries of the standard model are Lorentz invariants. Clearly, our space is not Lorentz invariant at all, right? And this is a real issue, right? If you want my answer, I just think we need much more time. And we need also a bit more open-mindedness of our community. People have an extreme focus on specific ways to make contact with, or try to make contact with the real world. but they're very slow to move. So the standard framework has always been, string theory has more space-time dimensions. We need to make them small, otherwise we would see them. We need to stabilize those dimensions in such a way that we would not observe them, and so on and so on. Maybe that's just not the right way to go.
Yeah, I see.
I mean, don't know.
Do you think that this is there because of the fact that I personally don't think that there is some scientific method that all of the scientists follow. But if you look at some naive scientific method that many of the children are taught in school sometimes, that actually has these steps that you hypothesize something and then you calculate its consequences and then test those consequences. But I think one thing which is not taken into account is that it is possible that to formulate a theory you may take decades, and this is sometimes that people don't understand that it can happen that in order to formulate a theory you may take a very very long time or a theory or to calculate the consequences of that theory. So probably that's why people say when when they see the fact that string theory has not made predictions in decades, they try to say that probably it's not right. So do you think that this is the reason, or are there other reasons?
Well, no. So that I'm very sensitive. I'm happy you say it like that because I'm extremely sensitive to this way of phrasing it.
Mm-hmm.
Okay, so let me rephrase the whole problem
Right.
of making predictions because it's something I
Actually,
strongly dislike the word. Yeah, sorry.
Sorry, I'm saying that actually I'm playing devil's advocate right now.
No,
This is
fully
actually
agree.
not my opinion.
This is not an attack to you. I fully understand that. Okay, so if you especially see what people are commenting on social media, so you want to see like the layman's opinion on string theory, and they say, "Oh, string theory doesn't predict the universe. It's just not a good theory," and that is so fundamentally wrong. Okay, so and what I'm going to say is independent of string theory. It should be true for any theory of quantum gravity, if there is any theory of quantum gravity beyond string theory. Okay, it is like saying the harmonic oscillator is wrong. No, what it's about is that you try to find a quantum mechanical description of gravity. Okay, that's quantum gravity. String theory is quantum gravity. That problem is solved. Whether that's a unique way to make gravity quantum mechanical, I'm not going to comment on, but let me just say we have one model here. Okay, now, what is, I don't know, a deep philosophical mistake to make, which 99% of all people out there make it, is that once you make gravity quantum mechanical, the ground state of that theory should be our universe. That is just nonsense. And I do not know where this comes from. I wonder whether it maybe comes from popular books and so on. So this is not how fundamental physics works at all, right? Let me give an example. Imagine I find a theory in which I can make gravity with electromagnetic fields. So what we say, Einstein gravity and Maxwell theory, we combine it.
Mm-hmm.
We can make that quantum mechanical, which is, what loop quantum gravity people would say, right? Oh, we start with gravity and we have a way of quantizing it. That also means that they can quantize, I'm just saying, Einstein gravity coupled to electromagnetism. Fine, but that's not our universe. So is that theory wrong? No, right? So what is very normal to fundamental theories like string theory, and that's how it works, is that such theories have, in a way, extreme predictive power because they are unique. String theory doesn't have a single parameter you can play with, but uniqueness lies in the ultraviolet at the highest energy scales or at the smallest distances. That means that if I would take a magnifying glass and I look at the universe, it looks completely unique. However, when I go to long distances, okay, when we coarse grain or whatever you want to call it, then we have to take into account, okay, what's the vacuum structure of the universe? Oh, sorry, what's the vacuum structure of the theory? Now, you tell me, which theory of physics comes with a unique ground state? In fact, none, okay? And the more fundamental theories, often the simpler the Lagrangian, the more insanely complicated the ground state configuration is. QCD is an example. It's a ridiculous simple Lagrangian, and it is a nightmare to understand its vacuum structure, yeah? So the right way to think about string theory, and I should not even say string theory, the right way to think about what you would call your favorite fundamental theory of all interactions, it should be a beast. That beast should be trivial, like its fundamental formulation should be utterly trivial. String theory is a good example. And then you want to calculate the consequences for the real world, and you will always get stuck. Why? You say, well, to find the real world, I should look at all the possible vacua of that theory. And in those vacua, I look at the theory that describes the fluctuations around those vacua. I should give various quantum field theories, right? So what we have learned, what string theory shows that it's so smart in doing, it's indeed a machine. You can take the machine and you shake it, and it spits out low energy theories coupled to gravity. And we know they are consistent. They're there, right? For instance, we can have we are very good when there's supersymmetry. So we can give you a lot of, I don't know, SUSY QFTs in whatever dimension coupled to gravity. And we know they can be UV completed, and they're out there, right? But it's just that the structure of all possible vacua, and therefore a structure of all possible QFTs, is highly complicated. And we do not know whether our own universe is in there. So if our own universe is not in there, you can say the following statement: string theory does not describe our real world. Yet, I believe, imagine somebody can firmly show that. I without any doubt, I will keep on studying string theory, because it's a machine that allows us to study the UV completion of quantum field theories coupled to gravity. And so maybe, even if I can show it doesn't describe our universe, who knows, I can learn a great deal from what happens when I couple a quantum field theory to gravity, and I want to study what happens when also gravity is quantum mechanical, right? And I think this is why, you know, that I'm a believer, but this is why I strongly believe the right approach is a Swampland approach. The Swampland approach is not so naive as the original way of doing string phenomenology, which was like, oh, you know, I need to reproduce our world, so let me start compactifying the extra dimensions and see what I can do. This is not how science works, right? Science has never worked in that order. Namely, I see what out there, this is what and let me find a theory that reproduces this. No, what you do is you construct a theory, and you just sit down and you see what the theory can tell you. And that is what the Swampland is about. The Swampland is asking itself, okay, this vacuum structure of string theory is going to be a complete nightmare. And by the way, this is going to be true. Let me repeat this. If it's not string theory, it's going to be true for any fundamental theory out there, right? Its vacuum structure will be a complete nightmare. And what you then want is to find patterns in that vacuum structure. And that is the goal of the Swampland program. And that's why I love it, because this program is trying to tell us, okay, let us look at this structure, the vacuum structure. Do we see patterns that we can understand at a deeper level? Right. And I believe that's exactly the missing ingredient of string phenomenology, that when it started like 25 years ago, they were not thinking like this. And that was a huge mistake. And yeah, sorry, I keep on rambling. I can go on for hours.
It's fine. I mean, I love listening to this, but what you are referring to as patterns, do you refer to Swampland conjectures as patterns?
Yeah,
Is this what you're saying?
Exactly.
Okay, I see.
For instance, what we can already show, and I think actually we should stop using the word conjecture, or if we use the word conjectures, we should be consistent and again, for instance, refer to holography as the ADS-CFT conjecture. Somehow, when I was a PhD student, it was called the ADS-CFT conjecture. And as I transitioned into a postdoc, I just noticed how people started flipping conjecture for correspondence. People react very allergic to the word conjectures. And I think they should do the opposite. They should be very happy when they hear the word conjecture. Conjecture means you're a safe person. You don't want to claim something to be true unless it's tested or proven, or it's tested to an extreme extent. And this happened with ADS-CFT. There's no proof. We are in need of a proof, absolutely. But we have gazillions of tests which go far, far, far beyond how things are protected by symmetries, okay? ADS-CFT stands an extreme special test, and I think the same has happened with, for instance, the weak gravity conjecture. So the fact that gravity has to be the weakest force comes out as a unique property of all possible string theory vacua. To me, that is huge. Okay. You could say, I already knew that.
Mm-hmm.
I observe in the universe gravity is the weakest force. Well, string theory is telling you it cannot be any other way, right?
Mm-hmm.
So there's
Yeah.
so many ways in which string theory is showing that it's absolutely making sense and potentially can describe the world. As I said, even if it does not, I don't think it's a disaster. You know, the Ising model doesn't describe a magnet. We know it, yet students, till today, all students in physics have to learn about the Ising model, right?
Right, because it's a simplified model
It's a
of a magnet to
simplified
some
model, and you
extent.
can learn from it. Exactly. Yeah.
Right. Well, one thing that you touched upon before, and we can talk about that a lot, is that you said that people on social media have very different, very wrong view of string theory, right? So do you think that, for example, if you look at, this is something that I was talking about with some of my friends, I think some weeks ago. If you look at early 2000s, at that time, there were a lot of well-known names who were popularizing string theory. But over the years, that has gone down. Do you think that's the problem? Because there is no significant figure that is popularizing string theory, and there are a lot of misguided critics of string theory that have become very popular on social media. Do you think that this is the reason because of which people have the wrong picture of string theory,
Right.
or there's some other reason?
Well, so you dropped for a moment, but I think I understand what you were saying. Well, it is definitely related to it, right? So string theory has received lots of criticism by some people who are very popular on media, on social media. And yeah, that definitely influences the public, right? Because imagine I am like a 14-year-old who is just very curious, who has picked it up, these words like unified theories, quantum gravity. I mean, that's how we were probably you probably like me when we were young. And then I went to the library. I'm an old guy, but nowadays you Google. And the thing is, when you Google, actually, indeed, the first hits you will get are of these famous string theory critics. But I also must say that I think it's important to criticize string theory. It is good. And I also believe that the reason we have so many string theory critics is also because some of the people that were advertising the theory in the past didn't do a good job either. And this is a back reaction. So when I was young, of course, I fell for it. And I think these books inspired me. But if you read what these books are claiming, it wasn't healthy either. Okay. So it's kind of a natural back reaction, but it's back reacting more than it should. And my biggest worry is I would be totally fine if this criticism would specifically be about string theory. But if you look at what these criticisms are, so much of it is almost being against curiosity. And I always invite people, oh, you tell me what's your favorite criticism from I don't know, Peter Voigt, Lee Smolin, Sabine Hossenfelder. Replace the word string theory in their criticism, replace it with any other thing that you know, which is like fundamental, I don't know, loop quantum gravity. You can just equally apply it. People that say no are lying. You can't apply it because if the main criticism is, oh, it cannot be tested, it's not physics. Sorry, that's first of all, not true. It should always come with a nuance. It cannot be tested with current day technology in any obvious way. Then it's not physics. That should be then the criticism. That applies to any theory out there who claims to be a unified theory of all forces in nature. This is because if you don't understand this, you don't understand basic quantum field theory, right? So imagine that somebody says, no, loop quantum gravity makes measurable predictions. Okay, show me, what are they? The fact that they cannot do it is because it better not. Because if it makes obvious predictions at low energies, there's something deeply wrong with quantum field theory. So to anyone out there, I want to say, if you read about this and you say, oh, string theory is such a bad theory, it's like philosophy, I challenge you to see whether whatever you're thinking about this, you cannot apply it to anything else that is supposed to be fundamental. And the answer will be obviously yes.
Right. I mean, what you just mentioned is that, for example, a lot of people have this criticism that string theory can only be tested at very, very high energies. Therefore, it's not testable with the current technology in a Well, they don't use this caveat, but it should be used in an obvious way. I mean, that criticism is actually about Planck mass being so high. So it's not just about
Exactly.
string theory, right? It's
Exactly.
about quantum gravity in general.
Absolutely. Yeah.
And one more thing is that even if you don't talk about Planck mass being too high, for example, I don't know if he's still actively doing it, but Sheldon Glashow used to be a bitter enemy of string theory. I'm sure he's still a bitter enemy, but he's not that active now. But the thing is that there was a very good point raised by Murray Gell-Mann in one of his videos, and it was that if you look at Howard-Georgi model, SU4, even those particles, the X and Y bosons in those models, can only be found at 10 to the power 15 GeVs. So even that cannot be tested right away, right? So if he's saying that string theory is not testable, his own model was, well, it was testable because of the proton decay thing to some extent, but I mean the X and Y bosons cannot be seen. So in his own model,
it's a pity that Shelley has gone on to be such an enemy of superstring theory. He's also helped to spread the entirely wrong idea that superstring theory can never be tested. What one could say is that the real unification that occurs in superstring theory does not occur until you reach very, very, very high energies around the Planck mass. And therefore, a direct test of the unified regime will not be possible. But that doesn't mean you can't test the theory. And what's curious is that Shelley participated in this move to discuss unified Yang-Mills theory with a higher group, SU5 or something bigger. And that theory, if it happens to have significant degree of truth in it, would also take effect only at very, very high energies, maybe 10 to the 15th.
And one more thing is that I don't know if you remember that video. There was this video some months ago by Sabine Hosenfelder, and she was talking about how particle physicists operate nowadays. And she was saying that they just invent new particles. And there were some people who actually came out with some of her papers where she too was doing this thing, that she was just inventing new particles to make sense of Mond to some extent, I think, if I'm not wrong. So the thing is that
that's true.
that's true, right? So as you were saying before, that most of these arguments are actually against curiosity in general, not just
they're
string
against
theory,
curiosity.
right?
But of course, maybe Sabine has a good point when she wants to say, hey, wait a minute. When you're a physicist out there in the game of trying to find physics beyond the standard model, yeah, this game can be played till eternity. So be careful. And I think that's something that every string theorist actually agrees on. And this is why it annoys me, because this is a fair point of her, but she's not selling it in any consistent way. Because what are string theorists doing? They're like, oh yeah, we absolutely agree. We don't want to follow the way particle phenomenologists are going. No, we are the people that want a UV complete. So we say we're only happy to look at some model beyond the standard model if we know we can get it from a string compactification, right? So no, not anything goes. Actually, for a string theorist, almost nothing goes, right? It has to come from string theory, and then it's very tough. So this is why we have the Swampland. Hopefully, it's a set of principles which particle physicists or phenomenologists can play with. And then if they obey those conjectures, they have a much higher chance of being able to UV complete their model. So to summarize this, I think Sabine at least has made a fair point, but it's a point, the part of it that's fair is exactly the point that has always been shared by string theorists. That's exactly why we do what we do. And so if you lump it together with her criticism on string theory, you just see that the criticism is completely inconsistent. Okay.
Right.
So, yeah.
I mean, she's criticizing something. So she's telling the string theory community something that they already agree on. I mean, it's not something that they disagree on with her. One more thing is that so Sabine, some of the points that she raises are actually respectable. I mean, there are some people who I don't just respect at all because, for example, Eric Weinstein's points are just, I mean, they are just misleading many a times. So I don't think that I agree with him on anything. But there's one thing that I wanted to ask you if you have any point of view on that. So a lot of this criticism on the internet, do you think that affects the funding situation of string theory, or do you think that does not make a difference?
Well, this now you're asking a very tough question, and I've been thinking about it myself.
Mm-hmm.
And I'm undecided on this.
Okay.
But I'm interested to hear. So the only thing I can tell you from personal experience, but then again, an anecdote is worth nothing if you want to make a claim about the general situation. Yet,
Right.
I'm going to make a mistake of making the anecdote. The anecdote is that, like my group, so we are when I say my group, I mean the group of Nikolai Bobev and Thomas Hertog and myself. We kind of work together as one group. We have been very successful in getting grants up until like 2014. And then suddenly, whenever we made a grant application, which was sufficiently formal, so really aimed at string theory holography, all the reports that came in looked like they were written by, Peter Voigt, Sabine Hossenfelder, like almost literal quotes out of these books. So the way I interpreted this was as follows. You have these grant proposal committees, and sometimes, it's a lot of politics out there. People want to get money for their community, and, everybody makes sure they have a person in that committee. There's a whole fight about this. I think it's almost never about scientific ideology in those committees, but okay, let me not go there. So these people with these books, they finally were given like the text that they could, like it's ChatGPT for them. They don't have to think about it too much. Like it was given for free. Hey, now I can say these words, and it will sound as if I make some sense, right? I think this is yeah. For instance, if people have said these words like, "Oh, we're not funding this because it doesn't have an application, to measurements directly, so it's not physics," and then those people would go out and then I don't know. Try to get funding for a project that is about the interpretations of quantum mechanics, which I think you should get funded. No problem there.
Yeah.
But honestly,
But the
if you
same
tell me
criticism
that
goes
it's
there.
the same problem, obviously, right?
Yeah.
Yeah.
But do you know any other colleagues that have faced the same situation as you?
So I think to answer your question is kind of easy. But I'm not the person that should have done that. So maybe you can judge it actually better than me. To answer the question is the same as trying to understand, is the community shrinking or growing? Because that is literally purely dependent on the amount of money that's in that is being given, right? I think our community is not shrinking. It is shrinking in the United States. There is no doubt. The US, yes. Europe, I would say no. But often we are a bit later than the US, so it could happen here. But yeah. So I think this is the exercise we should do. What clearly has happened is that when you say the word string theory, I think it has become broader. Like people doing very heuristic approaches to quantum gravity. Say they use like notions of quantum information theory. Some of us would call them qubitsers, right? So the qubitsers themselves refer to themselves as string theorists because their intuition comes often from holography. But that community clearly has grown at the expense of the formal string theorists going down, but yet they label all of themselves as string theorists. So in that sense, I think the string community has not really become that much smaller. When I speak for my own country, which is a super tiny country, Belgium means not much. Yet what I see, and this is not good, is that in the past, the way grants were given, and I'm talking specifically about PhD grants that are essentially PhD scholarships, they would be given based on grades. A student would, graduate from a university, the top student would often get, like automatically would get a grant. And what has happened is, and I don't think that's good, but I'm just saying what it is. Like in physics, usually a big chunk of the top students of all universities went to theoretical physics, and then within theoretical physics, they would go to string theory. Okay, so this has always annoyed people. And what has happened recently is that, and that's a modern trend, is that now even PhD scholarships are given to projects. Like a student has to claim that they can write a project to solve a problem, I don't know, in theoretical physics, and then a committee will not judge the grades of the student, will judge the quality of the proposal, which again is is very unfortunate. You cannot expect from a student who just graduates that they can write a grant proposal, that they have this big vision on a huge on a research problem, right? So no, I think when students get a scholarship, it should be purely dependent on the qualities that they have shown as a student.
Right.
They should earn
Because
it, so to speak. Yeah.
one thing, I don't know if you agree with this, but I have seen a lot of people working on string theory who actually don't like to be called string theorists. They say they just call it theoretical physicists. We work on string theory. That's one of our things, but it doesn't mean that we will only work on string theory, right? So I think that also goes for the students, right? That it doesn't mean that if they're working on string theory, it doesn't mean that they're only working on string theory as well.
Because the tools needed to work on string theory, as you know very well, is like, conformal field theory. I mean, actually every aspect, maybe not directly statistical mechanics, but there's so many aspects of theoretical physics that are involved in string theory that when a student does a PhD in string theory, I think the student should be able to go any direction within theoretical physics. Also vice versa, we should be able to get postdocs that have not done a PhD on string theory, but are just knowledgeable. They should be able to work on string theory in their postdoc, no problem. Yeah.
Right. And one thing that I actually wanted to talk about right now is that you just said that our community is not shrinking. I mean, you said that in the US it's shrinking, but not in the Europe right now. But so there is something that at least the students of my age listen a lot, and it's that the number of positions in high energy physics are actually dropping. So do you think that that's actually true? And the second thing is that if that's true, then is it because the funding is decreasing, or is there some other reason?
So it's a very good question, but I think it should be continent dependent, the answer. Okay, and unfortunately, I'm most knowledgeable about Europe. So I would say that the number of faculty positions in the US is on a decline. I think without any doubt, you can just see it, the way they hire. In Europe,
so faculty positions in general, not just high energy.
No, high energy. Theoretical high energy. Yeah, not in general. But what's happening in Europe is the following, that, and I dislike this a lot, universities grow because the number of students has been growing a lot. And this is because of two reasons. Almost all high school students are now going to university. That's one. Secondly, there's a lot of international students coming in from outside of Europe, which is very good. I mean, there's so much talent out there in Asia, and I'm sure soon, Africa will follow, and there will be a huge inflow of Africans. That would be great. And so that means that the universities are growing, but the number of professorship positions, so faculty positions, are not growing. They, like, at least in Belgium, they're frozen. They will always remain the same. And that is indeed bad for younger people in our field, for the PhD students and for the postdocs. Why? Because it means that the academic pyramid is getting flatter, right? So I think when you say students worry, the worry should not be expressed in terms of what's the number of faculty positions. It's more, how flat is the academic pyramid? Because first of all, the universities are growing. Secondly, the population of the Earth is still growing. So everything should grow. And the pyramid should not get flatter. Yet they freeze a number of faculty positions. And I think they do this because the most expensive positions at the university are faculty positions. And so one option to solve this problem, and I would be completely in favor, is that we rethink salaries.
Okay.
So this hierarchy in salaries should probably not exist as much. I think, if we can relax that, maybe universities will be less reluctant to hire faculty, to hire more faculty. Yeah.
Well, I mean, but one can say that faculty members also bring in money by grants or stuff like that.
No, they bring in research money. But they bring in grants, and then grants can never be used to hire faculty. So the more, this is actually the cause of the problem. Like Germany and Austria are the worst countries in this respect. They focus so much on young people who can bring in big grants,
Right.
And then they refuse to increase the number of faculty positions. So in those countries, the academic pyramid is even more insanely like this. And what is the worst of all, the layer exactly below the top, let me call the top just the people with a complete permanent position. That layer is doing all the research in Germany and Austria. They bring in the money like ERC grants, and yet they're not given permanent positions. So when young people are worried about the lack of job security, I agree, I support them. And one option that I see is to change the salary system. And then universities might rethink the hiring process. Yeah, that's one option. Yeah.
I mean, but actually, yeah, one thing that I said is that they bring in money through grants. But one more thing is that if there is some faculty member who does quality research, then university can advertise that research and attract more funding from their, donors or something like that. So do you think that this is another way in which faculty members can bring in money so their salaries are probably justified?
Sure. Yeah, true. Yeah, sure. In that sense, what you're saying is that take a typical university, the people that bring in money, which the university actually also gets from the overhead, indeed tend to be faculty members. Yet, and that's my worry when we talk, for instance, specifically about Germany, which is a big player in Europe. I would say most of the funding, the grants in Germany, come from people that are not fully permanent. They're like, young professors, I would call them, of my age, yet without a permanent position. So they bring in the money, and after the ERC grant or whatever grant is gone, they can go. Like, bye-bye.
So they're not rewarded for their work.
Well,
right?
they're not given job security, and
Job security.
they're put in the private industry or whatever, private sector at an age of, say, 45. You don't do that to a person, okay? That's extremely tough.
Right. That's tough, yeah. Okay, so actually we I don't know how we stumbled upon this whole topic, but the one thing that we were talking about before is that you were providing that anecdote that you actually got rejections for some of the grants that you were talking about. So one thing that I wanted to say is that there was there are many reasons to like Polchinski, but one of the things that he did that I liked a lot is that he actually used to reply to criticisms of string theory, however bad they are, right? And I don't know if somebody has filled his shoes after him. Do you think that if somebody has filled his shoes after him, or do you think that we actually need people to actually write popular accounts of replies to these criticisms so that public perception can be better?
It's an excellent point. So there are people like me, but the problem is we don't have the weight of Polchinski, right? So we should look at the real stars in our field, and they should. Polchinski was definitely one of the big stars in our field. It's very unfortunate he's not there anymore. Somebody should. I totally agree with you, right? And yeah, it's not happening. I agree. It's not happening, unfortunately. I mean, Joe Conlon wrote a nice book, Why String Theory, but that's it. I mean, it's not that, people are writing blogs now about defending string theory, or at least not defending it. That sounds bad, but at least attacking the bad, cheap criticism out there. Because now the people with have very cheap criticism, they're just, there's no resistance for them. They can just go and, influence everybody out there.
Right. That's true.
And so the people standing up, like before, for instance, there was a blog by Lubos Motel. Of course, that was convoluted with a lot of extreme political takes, which then, takes, for many people, it took away his credibility, right? So yeah, I totally agree, and I don't know, one person that if you talk to who can do it very well in person is Kumrun Wafa. He would be and he's a strong believer. It just that I understand he's a pure researcher. He wants to focus so much on research that he doesn't find the time, I guess, to start reading these books, and I cannot blame him.
Yes, I mean, Kumrun Rafa is. I agree that he is a very good person to do it. I think at some of the at some of the platforms he has done it, but I mean, we need much more from him. Another person who actually, I don't know if he attacked the criticisms, but he popularized string theory a lot, was Brian Greene. and
Yeah.
now he's doing other stuff. So I don't know if he will find time to do it.
The thing with
I
Brian
think,
is that I think,
Mhm.
I mean, I read this book when I was young and I loved it. But when I said that some of the books sold string theory a bit wrong, was also Brian's book. So he lacked some nuance in his books, which opened which essentially are sourcing the criticism, so to speak. And the problem with Brian, all respect for his papers, and he still has some papers once in a while, but you can tell that he's not an active researcher anymore. I don't think you
Yeah,
can call him an
I
active
don't think
researcher
he
in the
is.
last 10 years. And no, we need somebody standing up like Polchinski did, was a full-time researcher, okay? Yet he took the time to indeed write in articles criticizing the criticism.
Right.
Uh,
I mean, because the thing is that if you're not a full-time researcher, people can actually use that fact against your credibility, that, oh, you're not even in the field now, so why should we believe you, or something like that. I think, for example, if you take if you look at Witten's take, I think he doesn't think that attacking such criticisms is necessary. So probably
yeah,
he's not going to do it anyway. But one thing is that I think uh, I don't know if stars of the field have to do it. For example, the people who are criticizing string theory, some of them are really big names. For example, Lee Smolin is kind of a big name in quantum gravity, but Penrose is a big name. He's a Nobel laureate. He's also a big, critic of string theory. But other people other than these two, they are not stars of their fields. I mean, they are just random people who actually got a lot of fame, to some
right,
extent, right?
right.
So the thing is that, do you think that the people who are actually, attacking these criticisms, they need not to be the stars of their fields either, right? They can be, I mean, even a PhD student with good understanding of string theory can do it, right?
Right. Yeah,
Right.
no, you're
So
probably right. I just thought it would be natural
yes.
if somebody famous, like genuinely famous, would stand up. No, you're right. I actually once made an attempt to write a 10-page popular article, and I don't know where I kept it. Where I really read Sabine's last book and I dissected it. And then I felt there was clearly the need for, indeed, as you say, somebody doing, like taking the time for doing this. Because there's so
Yeah.
much misinformation, also on basic things in high energy physics, which are super interesting. And then I realized they're not explained. So let me not even say that somebody has to stand up to do outreach about the wrongness of the criticism. What I feel is there's the need for the outreach of certain topics that everybody talks about. Yet maybe you can correct me. I do not know of a single popular book where it's explained. And let me say what I mean specifically. It's the issue of naturalness, what is called fine
Oh.
tuning. Okay, so at the heart of all that criticism is this. And these are non-trivial notions in quantum field theory. I think, of course, they exist outside of quantum field theory as well. And yet they form the inspiration for things like the multiverse, the landscape. And that even, I can pick a 14-year-old from the street with a skateboard and they might have heard about the multiverse. They haven't heard about naturalness, but they need to know that these things are
Yeah.
invented because of naturalness, right?
Right.
So,
I mean,
yeah.
people who are more in the who are more interested in the philosophy of physics, they know more about naturalness than, people who are more interested in physics
Right,
many
but
times.
somebody needs to explain the idea of naturalness and
Yes.
fine-tuning and the cosmology constant problem, the weak hierarchy
Right.
problem, because they're at the core of all of these discussions.
I don't know if you have you read the book Puzzles to Unravel the Universe by Komron Baffa?
I should, but I didn't. No.
Oh, okay, so yeah,
Yeah.
so that book has all of these topics. It has
Really?
naturalness. Yes, it has. And the great thing about that book is that it uses simple logic puzzles, and then he connects them to different topics in physics. So yeah, he talks about naturalness. He talks about, I mean, cosmological constant problem is actually discussed in many other books as well. But yeah, he does talk about naturalness.
But
But I don't
okay,
know.
so Kumron's book, I definitely should read it. So it's good that you remind me. But when you tell me that there are other popular books discussing the cosmological constant problem, sorry, I haven't seen a single one that does a job at actually trying to explain it.
Okay, let me think if I can
because it's a
recall some book
highly
from,
non-trivial
right.
problem to explain.
Well, okay, so if I say a book explains cosmological constant problem, what features of the problem would you like it to address?
The sensitivity of vacuum energy
Okay.
to the physics in the ultraviolet.
Oh, no, that's not addressed.
No, but
You know,
that is
right.
absolutely crucial, right? So without
Yeah.
that, you should even ask the question, what on earth are string theories doing trying to understand the cosmological constant problem? It is like a it's like a geologist studying the standard model to understand problems in geology. It would just not make sense,
Right,
right?
exactly.
And the reason we do is because it's a relevant operator in a way. You could say it defeats the decoupling principle, and this is why it what you should think of as the lowest energy scale known in physics. I don't know anything that is as small as an energy scale as dark energy. Yet its explanation requires the highest energy scale in the universe, namely everything beyond the cutoff of the standard model. Yeah.
I mean, correct me if I'm wrong, but I think, for example, in string theory, cosmology and particle physics are very interlinked. I mean, if you start with some vacuum,
Exactly.
and if you add some of the particles in it, you have to recalculate if the the vacuum is, I mean, is close to that original vacuum, but it rarely is close to that original vacuum. It's sometimes many times it's very different, right? So this is what you mean when you say that cosmological
Absolutely,
constant
Hassan.
problem
I'm
is
so happy you say
right.
this. To me, it's when I, as a postdoc, started to realize these things a bit better. That's when I got so convinced that string theory is the right framework. We in the calculations, it's impossible for us to disentangle particle physics from cosmology.
Right.
Whereas the history of physics has worked like you can decouple them.
Yes.
And so it's great that string theory, that clearly shows how powerful it is. That it's so. This, by the way, this is the hard why it's hard to make predictions for non-supersymmetric situations. The fact that we cannot decouple cosmology from particle physics in our calculations, it means that we have to do all at once. And people cannot appreciate this. And I believe anybody who ever comes up with something they call fundamental will face this problem, right?
Yes. I mean, I think there is another way to say this, which is that if you calculate pair cosmological constant in string theory, and if you are in the region in the modulus space where the string coupling is really, really small, and the volume is, I think, really large as well. Large as well. Then I think that pair coupling constant, sorry, not coupling constant, cosmological constant is very, very close to the actual coupling. Cosmological constant. So I think that's a very interesting feature of string theory. I mean, that's something that you don't find anywhere, I think, except string theory,
Not that I know,
according to my knowledge. Yeah.
No, it's true. What you're saying is the following: that there are regimes of the theory where we can actually compute the full blown renormalized cosmological constant, so the full vacuum energy, almost by a classical computation. And that's something that a quantum field theorist could never, ever dream of, ever, by construction, right? For that, you need a UV complete framework. And that's what I mean, that I don't care too much whether string theory in the end describes our actual universe. Of course, I care, but the fact that I can study this question, oh, here is a quantum field theory, let me couple it to gravity. Oh, can I actually compute the full vacuum energy? Because a quantum field theorist to say, no, I can just add this constant to my Lagrangian. I can do it without getting punished. String theory, no way, impossible to do this. So somebody gives us a QFT. Well, we say, let me see whether I can get it from a compactification. And then we uniquely give the vacuum energy to that person. Okay. So if that is not an amazing property of the theory, I don't know what is, right?
Yeah, I mean, you just said that no quantum field theorists will dream of it. I'm sure they will dream of it. It's their dream if they could do it, but they would not try to do it, actually.
Right. So actually, I wonder whether people like Weinberg or Penrose, whether they are even aware of these, facts.
I don't know.
No, I doubt it. So when you say that Penrose is a famous person who stands up against, the moment they stood up against, they were not really into active research areas which would deal with this. So that I personally, I know they're geniuses. I don't think they can judge string theory because they haven't done it. They haven't properly studied it.
Yeah. I mean, for example, Penrose's criticism just ends at he says that you have a wrong number of dimensions. That's it.
But the trouble with string theory is it's supposed to be a theory of the way the world operates. And if the number of dimensions of space is just wrong, I can't take it seriously. And I mean, there are arguments why all these extra dimensions are hidden, and I don't think those arguments are right either.
That's it. I mean, he
But see,
literally
this
said
to
that in
me
a
is so
conference.
crazy. It's so insane. I personally hope that, imagine somebody comes with a proof that string theory is wrong. Okay, wrong again, meaning that our world is not a solution of it. Then when they come with an alternative and that alternative doesn't have many more dimensions, I will be highly doubtful it's a good theory, right? So again, and the reason is very simple. So let me just mention this once more because I think it's an absolutely crucial point. If a theory is to be fundamental, it should not come with any parameter. So then, in order to be able to describe a lot of physics and something as complicated as a standard model, it must mean that it has a rich vacuum structure.
Yeah.
The good thing of relativity, of gravity, is that when there are, the more dimensions there are, the more non-trivial vacuum structure of solutions, like the vacuum manifold is. Okay, so this is a point I try to explain to people often. So imagine for a moment, let's forget string theory, let's do the old Kaluza-Klein idea. The universe is 5-dimensional, okay? And people say, wow, that's obviously wrong. I would say no. And there was a recent Twitter fight I had with actually philosophers. I think there is more evidence, and this is a claim I actually want to hold on to. There is more evidence that the universe is higher dimensional than the universe is 4-dimensional. And let me tell you why. Sure. If I have a 4-dimensional theory, in the sense that my Lagrangian at the high energy scales is 4-dimensional, which is apparently what Penrose wants for some dark reason, then most of the vacuum of that theory will not be 4-dimensional. If I take a theory which has, say, 5 dimensions, in its UV description at the highest energy scale, there will be a few vacua which are like 5-dimensional. And then there will be a shitload of vacua which will be 4-dimensional, 3-dimensional, 2-dimensional. You see?
Right.
So this is the whole point. And I think people like Penrose just haven't understood this basic point. A theory with more dimensions than 4 has many more vacua which are lower dimensional than vacua which are higher dimensional. Right? So actually, the moment GR was developed, people should have already asked themselves, wait a minute, we're so lucky the universe is 4-dimensional because now that we know there is GR out there, our theory has so many more vacua which are definitely lower than 4-dimensional. And we would not exist, life would not be possible. So to me, that's where I would use anthropic principle. I know the standard model is coupled to relativity. I know this means that there is an amazing amount of 1-dimensional, 2-dimensional, 3-dimensional vacua.
Right.
And if you ask me, why are we not living in those? Well, to me, that's clear. That's anthropic reasoning because there's no life possible in those vacua, right?
I mean, there's another argument which people put out forward sometimes. They say that if you well, I don't know about life. It's hard to define life, but if you want us to exist in those vacua, then the thing is that if you look at DNA, and DNA is knotted, so knots untangle in dimensions more than 3. That's why, I mean, that's another reasoning. That's also anthropic reasoning, but it's a more detailed anthropic reasoning. So yeah, that can be another reason. But then someone might say that, okay, if you just want some theory which has more than 4 dimensions, then why stop at 10? Just go to 100 dimensions or something like that. So, I mean, that again will start, a race that you can
no, because I
with.
would say that a fundamental theory should kind of have a preferred number of dimensions. No?
Okay. Well, I mean, again,
but I'm not sure you should say that of string theory. I think it is too quickly say that string theory has 10 or 11 dimensions. But I also have to admit that I'm not sufficiently knowledgeable about this fact of string theory to have a strong opinion. But there's, of course, what we call non-critical string theory, right? Which is outside of 10 dimensions. Also, when we say 10 dimensions, I think we should be really careful when we popularize string theory, I wouldn't call them dimensions. They don't have to be spatial dimensions, right?
Yes, exactly. This is something that I have written about a lot. I mean, probably not on Twitter, but somewhere, because it's central charge. It's not dimension. It does not need to be a
Exactly.
dimension.
Right.
And I don't know why this point is not addressed in popular science, that it does not need to be a dimension. It can be, I mean, you can fulfill the central charge by adding some other CFT, which is not just the free boson or something
You
like
can
that.
use a critical Ising model.
Oh yeah,
And you
exactly,
cannot
exactly.
interpret it as No, I think so. This is a good question. So I guess the reason people haven't popularized this is because it's so abstract. And I once thought of how should I popularize it, and I think I would use the word junk. Okay,
Junk.
so
Okay.
string theory says there are 4 spacetime dimensions plus junk. And there are corners of the theory which are junk is exactly 6 extra spatial dimensions. And there are corners of the theory where it's something else. But actually, it doesn't matter whether it's space dimensions or something else, because the smoking gun of that junk is always the same. It would appear to a person in 4 dimensions as towers of particles. So meaning very heavy particles, which come in towers, meaning that if you have a particle with mass m, you probably have a particle with mass roughly 2m and then roughly 3m until infinity. Okay?
Right.
And that is true for whether that junk to get supercritical strings defined is 6 extra space dimensions, or whether it's something as abstract as, I don't know, some CFT with the right central charge to cancel the total central charge. Yes.
I mean, when I popularize the central charge thing, I just say that it's a property of the theory. That's it. I don't know how to say it. I mean, it's hard. It's really hard.
Right. It's like the
Because, I
rescaling
mean,
symmetries of the world sheets have to be obeyed quantum mechanically because you gauge. No,
yeah,
it's super hard to explain.
it's super
I
hard
agree.
to explain. Yes.
Yeah.
Right. So I think probably that's why, a lot of popularizers of string theory just use the word dimensions. And one other reason is that, I mean, if you popularize higher dimensions, people will be interested. That, oh, you have higher dimensions. That's interesting, right? There was a question that that was coming to my mind. I think I forgot it now. Okay. So it's about another thing. I think I read that paper of yours. I think it from 2018. What if string theory has no deSitter vacua? I think that's in 2018, right? So I think there you wrote this thing that we probably should try to understand CFT landscape first. That can be coupled to ADS, because you also, before that you said that we should try to understand ADS landscape, and then you wrote that some people claim that it has been found, but by landscape I mean that where cosmological constant is small, right? So do you think that that particular approach has had a lot of progress, or do you think that it's still unexplored?
Excellent question. So let me rephrase a bit what you said, for in case people don't know what we're talking about.
Sure.
So sometimes, so I have to be careful. I have used the word landscape, say, not in the way that others have always used it. So let me first make it precise.
Sure.
When people in the media have used the word landscape, they generally have in mind a set of solutions of string theory which look lower dimensional. Okay? Whereas many vacua of string theory will look like, I don't know, a 4-dimensional space times a 6-dimensional space, but that 6-dimensional space is, maybe it's compact, so periodic, but it's as big as that non-compact space. And what do I mean with big? How can a non-compact space, you say a non-compact space like our universe is clearly infinite dimensional? No, that is not true. So when we associate a size with our universe, we talk about the Hubble scale, like the observable, like at which point is there a cosmic horizon that makes everything dark because things move away faster than the speed of light? Okay, that sets a length scale, which in a GR language is literally the curvature scale of the universe, right? So, and when I've used the word landscape, I generally meant solutions to string theory where the size of the extra dimensions is much, much smaller than this Hubble scale of our observable universe. Right? And so, to be honest, I almost completely turned to this question instead of this question of deSitter. Because I think what you should answer first as a phenomenologist, and this is why I love the Swampland program, it's allowed again to ask simple questions instead of like detailed questions. So instead, like, I'm more concerned about the question now, can we get a small cosmological constant out of string theory? And that question is identical to what I just said before. So a small cosmological constant means a large Hubble scale, large compared to the extra dimensions. And when I say a small cosmological constant, I mean small with respect to some fundamental scale, right? And so this notion in string theory is called sometimes scale separation.
Yeah.
Meaning that the size, well, the Hubble scale is so much bigger than the size of the extra dimensions. And the question is that possible? Because that looks like very unnatural, right? So indeed, this question ties to what QFT people have called naturalness. And the weird thing about string theory, but it's not true just string theory, I think it will be true for any theory with extra dimensions, is that it either has, as I said before, a huge amount of lower dimensional vacua, and then it's literally huge, right? Or you say, well, no, or it's the other way around. All vacua are maybe lower dimensional, but they're like in this stupid way, like, you know, there's a non-compact universe with a certain Hubble scale, and then there's a compact universe with an equally big radius. An observer in that space would always say they're not lower dimensional, they're higher dimensional. They would see all the dimensions, right? So, and the thing with string theory is the following, that it gives us glimpses that indeed there seems to be a huge landscape of genuinely lower dimensional vacua, what I call scale separated. But what is funny in a way is that when we try to construct them, that's exactly when we don't feel comfortable working with string theory anymore. Like, it's a problem of us, not the theory, that we have to rely on approximations which we are, you know, debating till infinity. So I don't think the community should so much obsess about this debate on the consistency of the deSitter space. They should obsess about the debate of the consistency of a small cosmological constant.
Right.
Whether it's
I mean,
positive or negative, I don't care.
Yeah.
I think we should do negative, because then at least we have supersymmetry to help us. We have holography to help us. And to me, I'm at this moment completely agnostic. I don't know. I don't know the answer. I've constructed vacua myself, which are scale separated, but I also see the approximations that I had to make in order to get them to work. And if people say, "Oh, I'm not comfortable," I cannot always defend myself too well. Yeah.
I mean, one, I'm sure you know this, but for the audience, let me just say that there is this no-go theorem by Maldacena and Nunes, which actually says that you cannot construct deSitter vacua using just the fluxes. The fluxes are just fields in string theory, right?
Yeah.
And you have to include these objects called orientifolds, which can be thought of as negative tension objects.
Right.
And if I'm not wrong, I think that theorem also applies to ADS vacua with scale separation, right?
Yeah.
Right. So I think they have also this problem as well. So I think they some of the people actually use something called classical ADS vacua to
Right.
work. So is this what you're hinting at when you say that
Yeah, so
use
we
approximations?
had a paper in 2015 just pointing out in a very simple way that Malacena Nunes can indeed be extended. So it also, like, it's a sense without these weird things called orientifold planes, which are objects in string theory with negative tension, which remarkably is consistent in string theory. Okay, that's another story. That without those weird objects, there don't seem to be any deSitter vacua for sure. I think without those objects, indeed, you can also show there are no scale-separated ADS vacua. That's a paper we wrote. It was a little heuristic, but then the same ideas have been worked out with much more precision in work by Tomasiello and collaborators. And I think they essentially come to the same conclusion. So morally, you're correct saying without orientifolds, we should not even dream about scale-separated vacua. And what I like about this is that you don't have to call it a string theory problem. You can give this to a mathematician, and it's an extremely clear mathematical thing that you can say, especially when applied to Freund-Rubin vacua. So the mathematical statement is the following. Is it possible to come up with a family of positively curved Einstein manifolds which have a say, and the property of these Einstein manifolds is that the curvature scale is fixed so that we can take it to be 1.
Yeah.
And can we, in this family, can we find like, and then you can study the Laplacian on this Einstein manifold, and you can ask yourself, what is the value of the first non-zero eigenvalue of the Laplacian? Is it possible to find geometries out there, Einstein geometries, for which this first number is arbitrarily high? Like somebody says, oh, I want it to be bigger than 1 million. You work, you find an example. Another person says, I want more than 2 million. At the moment, so this is a mathematical question, which I think is very exciting. There has been a conjecture by Yao and Vafa saying that's impossible. And to me, this is nice. It shows how thinking about string theory also leads you to think about pure mathematics. And I'm sure mathematicians are interested in this question.
I mean, string theory has a history of producing results in pure maths. So that's a whole topic to discuss, right?
Unfortunately, in this case, it's not producing a result. It's suggesting a very interesting question. And it actually suggested a conjecture. And I probably shouldn't use this to advertise my own papers too much. But if you're saying that string theory suggested solutions, we have a paper in which actually string theory seems to suggest a mathematical trick to find such solutions, which then to find such geometries, which would go against the conjecture of Yao and Vafa. But to make that precise, that's another story. So, but at least it shows how string theory can sometimes outsmart you. But I'm not saying our thing works. I think there are clear indications it could work, but I know other people have objections against it.
Right. There's one thing that I don't know a lot about this stuff, but this point seems interesting, so you can elaborate on that. If I'm not wrong, I think if you have some non-supersymmetric ADS vacua, is it true that open strings can actually destabilize them?
Not necessarily open strings. So I think that the status we have now, when you talk specifically about stability, and it's an important question because when ADS vacua are not fully stable, it looks like we don't have holography for them. Like there's no clear holographic description, and that's important for us to get a handle on.
And I think that's the reason because of which you might not have DS-CFT correspondence as well, right?
Exactly. Very good point. I totally sympathize with this. I don't believe there is a DS-CFT correspondence for exactly that reason. But yeah, so you're asking, so the situation in string theory so far is that every non-SUSY ADS seems to always have some decay channel. So that decay channel is often non-perturbative. So that means that if you're an observer in ADS, you're okay. You're not going to die immediately. You might have to wait a few billion years. But yeah, that's a conjecture that kind of seems to work. I agree on this. It's not always open strings. It can also be closed strings.
It can also be closed strings. Okay, that's interesting. And there's one more thing that I think I just glossed over that, but I don't know a lot about that. Again, it's not exactly theoretical. It has something to do with some cosmological observations. So I read somewhere that it's possible that string theory has this prediction that there are no tensor modes in the CMB. Is that correct? Is that actually a prediction?
Depends on what you mean a prediction. But I'm happy you ask it because I've said it in the past, but I'm not the only one. So in the old school way of doing string phenomenology, so this was pre-Swampland hype. The way people worked is that they say, okay, cosmologists or particle physicists say that this is a good effective field theory to get. It can do a lot, right? Inflation, cosmologists were telling us, oh, inflation is amazing. It can solve so many problems in cosmology. And then so string theorists would go say, okay, let me get inflation from string theory, right? And then they would hit their heads against the wall because it's so difficult. But then people started to get at least glimpses of how it could work, of getting inflation. I don't think there's a fully fledged inflationary model out there at all in string theory. But what I do agree on is that every intuition we have about how these models work. So you can always like sketch how these models should work. What you notice is that technically These are always they're never what we call large field inflation models. And
can you say it again? I think you cut out something. The
sorry.
internet was cut
So
out.
technically, what you can see, there's an intuition that this string theory inflation, if it exists, that's important, it seems almost impossible for it to be large field inflation. And large field inflation is a technical word for having inflationary models which give a measurable tensor modes out there in the sky. And so I think this is a complete missed opportunity in our field. We should have, like when these measurements like bicep were about to happen, we should have given a press conference saying, if they find something, we will urge them to look again at their data because we don't believe it's possible. Imagine. So I think we should have done that. We would have gotten so much respect. Instead, what happened is the exact opposite. The exact opposite has happened. A year before, 2 years before, a few people in our field, which by the way I admire a lot, but I think I'm welcome. I'm talking specifically about Eva Silverstein, Leah McAllister. They're amongst the top people in our field. There's no doubt. So let me be clear on this.
Right.
Yet, I think they went too cavalier, and then they said, "Oh, we see glimpses of models how it could work. Now we know that these models don't work. Sorry, we know that like they don't work, and without them saying this, we could have genuinely made that claim to the community out there. In fact, Joe Conlon made this claim in talks before Bicep came out. He said no tensor modes, and unfortunately, it kind of, I don't know. It's a huge missed opportunity for our field. I absolutely
That's
agree.
interesting. I mean, you just mentioned McAllister. I just reminded of the fact that he had some papers, I think 2 years ago, where he actually constructed a cosmological constant that was actually too small. It was 10 to the power negative 143, if I'm not wrong, right?
Yeah.
So actually, I still have to read that paper, but I think that was an interesting paper.
Right.
So one more thing that I wanted to say here was that so in the last probably almost 10 years, but I think 8 years, I think that's more precise. So for the last 8 years, or probably less than that, there have been a lot of works on something called generalized symmetries, including non-invertible symmetries and two groups and things like that. And my advisor works on that a lot, and probably I'll do one project with him where we will do that. So do you know that if these developments can actually help in understanding the Swampland program or something, or string landscape or not?
So I must first of all admit that I didn't really follow this. I mean, I sat through various talks about this, and to me they were very formal. And till today I don't understand the motivation or the interest of people in this. But I think that's okay. It's not because I don't understand. People shouldn't work on it at all. So you're asking something about which I don't know a lot. I can just tell you what comes to mind immediately, but I'm sure it's the same what comes to your mind. Yes, symmetries are absolutely crucial for the Swampland program because you could say that the most important conjecture of the Swampland program is that there are no global symmetries in nature the moment you have gravity.
Yeah, right.
So, and I can imagine that the moment you have non-invertible symmetries, the story gets a little bit more tricky.
Yep.
And then so far, whenever we have talked even about the most abstract symmetries, just checking this conjecture or checking what the consequences of this conjecture are has shown to be very important. Okay, no matter whether it's abstract symmetries. For instance, I have a paper on higher form symmetries, which people say, oh, that's a bit abstract. It's surprising that if you ask if the theory doesn't have higher form symmetries globally, when you couple to gravity, you actually conclude non-trivial things out of this.
Right.
So yeah, who knows? And I'm sure there are already papers out there, but I haven't followed them that have applied this to the Swampland.
Right.
Actually, now that you say it, I think I've seen some work, perhaps. So maybe like Ben Heidenreich and maybe some names. Yeah, I might have looked at this actually. So I'm not
I
sure,
mean,
but
so
yeah.
higher form symmetries, as you mentioned, I think they're one of the generalized symmetries. But
Right.
there are, for example, so when we think of symmetry, most of the time we think of group symmetries, but I think these are categorical symmetries or something like that. So that can be, as you said, that it can be a very tricky picture if you just generalize the symmetries that you have. So
Right.
yeah, so this is something that I'm a bit interested in, but I'm not very knowledgeable about these things. Okay, so I think my questions here are done. So thank you so much for your time.
It was my
And it was
pleasure.
very nice. My pleasure to talk to you as well. So it was very nice to talk to you.
Same.
Maybe sometime in the future we can have another session like that for some other topics.